You can see there's some bubbles there. Not huge, but there's a little bit, and that's just a 9-volt battery. Alright, let's disconnect that, and let's plug in just a plain old battery charger. This is going to get some amperage going through here. It's set on the 2 amp setting, but it's seeing this pretty much like a short circuit, so I think we're going to end up with a lot more than 2 amps going through this thing, but here we go. Now we've got gas production. So I'm thinking I need to be doing some sort of current limiting here. At that level, I would think it's probably enough almost to run like a generator engine. That's some serious gas output there. It's all hooked up for something else right now, so I just ran this recently and there was no problem. I'm going to assume it's good. We'll get a little bit of a spark when we connect it at the battery anyways. Okay, so here we go. This meter's reading current, and yeah, we've got sparkage. We are connected, so you should start seeing gas. There we go. Now that to me, from my experience, is quite a bit of gas for just plain old tap water. And if you look down here, we're drawing 8.4 amps. That's a lot of current. The water in this town must have a lot of things in it that are conductive to be drawing that much current. Couldn't I do this with using less surface area? There's 22 plates in here. What if I just use 2 plates?
It's got the washers, so they're not touching each other.
And there's neoprene tubing in between every plate on both sides.
Yeah.
To make sure they don't touch each other. But you can see how efficient it is, and that's just tap water. So what I'm testing right now is how can I minimize the current draw without having to make an electronic regulator circuit. So if I go down to just a 2-plate system, which I have, it's all been cleaned with acetone and just kind of strung together. These plates are farther apart than my other unit, the 22-plate unit. I'd say that's probably 3/8 or ½ an inch apart.
Yep.
Now, this is still just tap water. And that's even more than I would expect. I mean, if you had distilled water, no impurities, probably you'd see pretty much a tenth of this. Start of a new series.
More plates.
We've got 14 volts and 0.8 of a teaspoon of electrolyte, and we're reading 320 milliamps. And let's pause this for a couple minutes and see if it goes up anymore and stabilizes at some higher level or whatever. And then we're going to add some electrolyte a little bit at a time and kind of see what happens to the current draw.
Yeah, all right, we'll be back. Okie doke.
Okay, so we're leveled out at 320, 330 milliamps of current draw with just plain old tap water. We're going to add some sodium bicarbonate, 1/8 of a teaspoon. Sufficiently. But now it seems to be leveled out at 290 milliamps with 1/8 of a teaspoon. So let's take the next step, and we're seeing 12.5 volts on the voltage here. So let's take the next step, go up another 1/8. Alright, so this is with a 1/8 of a teaspoon, 2/8 of a teaspoon, 1/4 teaspoon. And we are up to 330 milliamps. We're still at 53 degrees. We're still at 12.5 volts. Reading. Alright, we're at 4/8, ½ a teaspoon. And it looks like the gas volume's maybe slightly higher. We're at about 425 milliamps. And looks like the voltage is up to just under 13 now. Alright, let's go up to 7/8. Alright, so hovering around 630 milliamps. Looks like gas production maybe a little bit higher still. Makes sense that it would be. And we're still at 13.2 roughly voltage. Temperature still 53. Let's bring it up to a full teaspoon here. Okay, this is a full teaspoon, 8/8. Gas production looks pretty respectable. 0.69 amps, 690 milliamps roughly. Voltage still right at 13.2. Alright, before I go up to teaspoon and a half, just want to make a note that we are seeing a lot of floaty stuff here cruising around on top of the water. 12/8, 1.5. And drying 940 milliamps. Oh, we're at 55 degrees over here. Whoa, we're starting to see some temperature increase with 1 amp. Or getting to 1 amp. Voltage is still reading a little over 12.5.